So we should start. Today we are going to continue talking about translations. I think that's where we stopped. Or rather, we just started a little bit. So let's try to get as far as we can today. So what we have is we have an operator, which I call script T. And this operator, by definition, is going to act on your position eigencat. So remember, this is the position eigencat, where the position operator now acts as the position operator. And when it acts on X, it spits out the location, basically, right? And what we're going to do is we're going to build up the corresponding translation operator. And so the definition, we should consider this as a definition, is that this is going to give me X plus G. Okay. So, for example, translation is translations commute, right? So if I go from X to X plus D1, then I go to X plus D2. I'm sorry, D1 plus D2. So this is, I add D1 to it, and then I add D2 to it. It's the same as if I get to X plus D2 first, before I then move again by D1. This is the same, right? I get to the same, this is the same location. So that means, for example, that T of D1, and then followed by D of T, actually D2 acting on X. Right, so this is D2 acting on X first, then D1 acting on X. Will turn out to be, of course, X. Let's write it step by step. So this is D2 plus X. And this guy acting on that will give you, X plus 2 plus D1, and that is the same, the end result is the same if you had reversed the order. Okay, just because translations itself is commutative, right? The order does not matter. This is something I hope is familiar. And therefore, you can conclude, unless you think about it yourself, but it should be fairly clear that translation operators commute. Okay, the operators themselves commute. So, not only that, we also showed the last time that T itself is unitary, at least when it acts on the space. So what we're going to discover is that when you deal with continuous operators, especially when it's dealing with geometry, rotations, translations, boosts, and so on, the geometry, the underlying geometry matters a lot. Meaning, what we'll discover is that, so let me just write it down first. So yesterday we discovered, not yesterday, Monday, we discovered that T dagger T was unitary. Okay, and basically the reason is because T of D dagger is basically, you can think of it as basically this guy acting on X, which is X plus D. Okay, and because of translation invariance. Right. So it means that if I have a pair of points, doesn't matter whether I go from here to here, or if I displace both points over here, this displacement doesn't change because space itself does not change with displacement. Right. This would not be true if we live in a curved space-time. Then translating it by some amount, you have to be very careful how you do it, which path you take would really matter. But it's not true in flat space, right? We live in approximately flat space. So,
is that the bra X plus D?
Oh, thank you. Yeah. So that when this guy acts on this, you find that this is X plus D, X prime. Let's do it, X prime plus D. And then when you add them together, you find that you get delta function of X minus X prime, which is just the identity operator in position space. So that's how we conclude that it was unitary, right? But because it's unitary, you can also conclude that if this guy, if T dagger were acting on X instead, then, so this, be careful that this is not the same as this. This is T dagger acting on X, whereas this is the dagger of P acting on X. So this, in fact, must be X minus D. Because this is, so we discovered that this is unitary, which means this is the inverse of T. And if it's the inverse of this T, it means that instead of translating it by D, you are translating it by minus D. So you're undoing this translation. Right? So this will give you X plus D, and then this will give you X plus D minus D, and therefore give you back X. Okay. So it's unitary. And if it's unitary, remember that if U is unitary, we showed this at least for the finite dimensional case, then U corresponds to, it implements a change of orthonormal basis. Orthonormal basis. And the way to remember it most easily is that is using this form of the representation, right? So you start from the old basis, the bra in the old basis, and then you write down the cat in the new basis. But now this is the sum over O times nu, sum over all the bases. So this is the same as saying U acting on the O basis, the I O basis will give you the I nu basis. Okay. And in this case, you know what's going on. So this is the discrete case, but in the continuous case, what happens is that you write down for translations, you write down can be in any dimension you want, so I put D. But of course, usually we're in 3. Usually we're in 3 dimensions. But the new basis in this case is just x plus D. And the old basis is just x. Right? So let me just write that down. So this is the new basis. And this is the old basis. And translation invariance basically means that even if I displace my x by d, there's no privileged origin, right? Who says that this is the center of the universe? There's no such thing, right? Why don't I call this the center of the universe? Or that, right? It doesn't matter. It should not matter what is the center of the universe. There's no distinguished, again, at least in flat space, there's no distinguished origin. So this is basically the statement. So there is no distinguished origin. That is basically the same statement as saying there's translation invariance. Okay, and that in turn is tied to the unitary nature of T, of the translation operator. Okay. I may have accidentally did the homework again. Anyway, yeah, probably. So now let's come to the construction of T itself. Excuse me. And what we're about to discover is that so we have one representation of T. This is one representation of T. But another way to write this is that T, because it's a continuous operator, is going to be related to the exponential of some operator. I'm going to just write it down. It's going to be D dotted into P. Right? So sometimes I'll write it this way, sometimes I'll write it as minus I dj pj, where there's an implicit sum over the j's. Okay, so D is exactly just the displacement vector. And the question is, what is P? Right, so we know, we expect that T should take this form, right, as we have discussed before, that whenever you have a continuous operator continuously connected to the identity, then you expect that it should take the exponential form. And how that's going to occur in this case is, firstly, let's make the observation that there is a continuous connection to the identity. And that's easy to see. Just when you make no displacement, there's clearly the identity, because when you act on X, it just gives you X back. Right? So clearly this is the identity. And because D is continuous, I can stick in any displacement vector I want. T of D is continuously connected to I. Okay. And that's why we expect that it's the exponential of something. So basically you'll discover in your homework that this is nothing but the Taylor expansion. Okay, so let me just write it down. So for homework, you're going to discover that this way of writing the translation operator, that this is just this just simply implements Taylor expansion. Okay, In other words, if you consider x plus d of some wave function, right? So remember we discussed this the last time, that psi of x, when you learn when you're an undergrad and you learn that psi of x is a wave function, what you discover over the past few lectures is that psi of x is really just one representation, is the component of the abstract state expanded in the position basis, right? That's really what's happening here. But this in turn, this amplitude, so to speak, can be thought of as basically the translation operator acting on x, right? This is just nothing but a definition of translation. But what you discover is that if you use this definition, you will discover that this is in fact just Taylor series. So we're gonna see a little bit of it, okay? And let's see how that happens. So we're going to see a little bit of it in the sense that I'm going to show you what happens if, for your homework, you're going to discover the whole series, but I'm going to just talk about infinitesimal displacement. Infinitesimal displacement. So it's very squeaky, but the ink is good, so I don't want to change the marker. But I don't like the squeakiness myself. So let's do it for infinitesimal displacements. So what I mean by that is I'm going to take d, but t, but not of d, but dc. Okay. So dc just means infinite. This is very small. And acted on x. And so that means this is just going to be x plus dc. Okay. And then I can of course project this guy on any state I want, right? So what I can do is that I can consider x plus dc of psi. So I take the wave function at x and I just consider an active translation to dc. But this, we discover, is x, this is just an adjoint of this guy, t dagger, but t, let's just write it down step by step, t dagger and then psi, okay? But what is t dagger? This is now psi of t dagger is e to the plus I d dotted into p psi. So you might wonder, hey, wait a minute, why isn't it p dagger, right? Remember, I'm taking t dagger, so this is minus, this was minus I, so it becomes plus I. D is real, and strictly speaking, I should put p dagger here. But remember, we proved that if t were unitary, then its generator has to be Hermitian. It's an if and only if statement. Right? So remember, u e to the minus I, some parameter c dotted into t is unitary if and only if t are Hermitian. I say R because T can be many, there can be many generators. In this case, there are as many generators that are dimensions. Okay. Now, of course, this assumes that C is real. And it is real in this case. Okay. So we know it's Hermitian, we just don't know what it is. We just don't know what P actually is. Okay. But now I'm sorry, actually this is DC. My apologies. I DC dotted into P. But now DC is very small, so I can imagine I can Taylor expand this exponential, and then just keep the first term, right? And then on the left-hand side, I can also Taylor expand this guy up the first order. So what does it look like? Let's come over here. So this is x. Remember, this is just a function of psi is now a function of x. So it's psi of x plus dc j dx dj x psi plus higher order terms, which I'm not going to care about for the moment because it's your homework. And then on the right-hand side, the rightmost side is x of psi. Let me write it as identity, because that's the first term of the Taylor expansion. That's the identity. The second term will be plus I d c j pj psi plus higher order terms. Sometimes I like to write of order dc squared. Okay, because the next term in the Taylor expansion is the square of the infinitesimal. So let me do it over here as well. Order dc squared. Okay. And so what you see is that on the left-hand side, I have x psi, and then I also have x psi over here, because this is the identity, right? The first term of the exponential gives me the identity. This action like this is x psi. So therefore, actually, this term cancels out with this term. And if I just compare the dcj term, okay, so the dcj coefficient is what is actually now dj, okay? And dj means dx dj. This is the shorthand for that. X of psi, that's the left-hand side, plus, equals I. So what I'm going to do is I'm going to multiply both sides by I, minus I. If I multiply both sides by minus I, this one will become 1, and I'll pick up a minus I here. So I get minus I, and this will be, in fact, x pj psi. So what we have discovered is that the generator of the translation is actually nothing but a derivative. Okay, it's just a partial derivative. The J generator of translation is nothing but minus I times the partial derivative. Okay. So this is the J generator of translations. And what we have discovered is that in position space, in the position representation, it is nothing but just a derivative. And so, like I said, for your homework, you're going to discover that if you actually plow through all the terms, right? So this is an exponential. So what happens when you keep the next term and the next term and the next term? So in your homework, you discover for yourself that if you keep all the terms, that's just nothing but calculus. It's just nothing but Taylor expansion. Okay. Any questions for me at this point? Yes.
So in this case, that you got something like a Schrödinger function.
Schrödinger equation.
And So you mean that the spherical
Yeah,
equation is just the first term of that
Yeah.
equation?
Remember that the Schrodinger equation on the left-hand side is not a spatial derivative. We're taking a derivative with respect to space here. In the Schrodinger equation, it's time, right? So that's the first thing that you want to remember. The other difference is that it's an I dt and not minus I, right? So this is minus I, but there is some similarity in the sense that I dt generates time translations, but time translations in physics is not just you go from time t equals to 1 to t equals to 2, but rather you have to know the dynamics, right? You don't just move in time. You move in time governed by whatever physical laws that you are governed by, right? So in some sense that's a good question. So maybe I'll just say a few words about that, right? So in some sense there is a relation in that sense. So this is space translations. But we also wrote down the time evolution operator, which is e to the minus I th, right? So if you compare, this is e to the minus I d dot p, right? And so this is in fact like time translations. Okay, but time translation is not just the Taylor expansion in time, because it's not a trivial, I just move from here to here, but rather time, we move in time. So physical systems evolve in time, governed by the Hamiltonian. Okay. In other words, it's not just I translate myself in time, in space, the way I translate myself in time. It's governed by the dynamics, governed by the physics. Yeah. Yeah, so there's something similar there, but not quite the same in terms of the underlying physics. Yeah. In other words, there's more physics here than here. This is more geometry. At this point, it's just geometry.
So that's Schrodinger equation from applying the same Taylor expansion like this?
It does evolve in time like a series, like a Taylor expansion, like a Taylor series, right? What you're saying is the following, right? If I translate myself by d, e to the minus I dp, then I can certainly write it down as an infinite series, right? I can term by term just keep applying, and then same thing as the Schrodinger evolution operator, e to the minus I th. Term by term is gonna time evolve psi step by step. Yeah, but again, remember there's physics here. Depending on what h is, the physics is different. But p is just p, right? P is just a derivative in that sense. Yeah. Okay. All right. So it turns out that this P is in fact related to the momentum. So if you've taken classical mechanics, you have seen a slightly different form of this statement. But essentially, you should have been told, if taken a more advanced course in classical mechanics, you should have been told at some point that the momentum is the generator of translations. And what you're seeing here is just a linear algebraic version of it. But of course, at this point, it's just a name, right? What is translating in space is just a P here, but what I call it is just jargon at this point. The reason why we call it momentum in quantum mechanics is ultimately due to the Schrodinger equation, which we will come to very soon. So how is this all related to the Schrodinger equation? Right? After all, we're not just doing math for the sake of doing math. We're doing this math because we are doing quantum mechanics. We need the linear algebra. So what you will discover is that in your homework, you will discover that the Laplacian, so if you do p squared psi in the position basis, p squared psi is of course, what I mean by that is just pj summed over j. And what you will discover in your homework is that this is just negative of the Laplacian. Okay, it's almost obvious. If you know what you're doing, it's actually it's quite obvious why. So this is the Laplacian. Okay. And so in the Schrodinger equation, which you might have seen in many times by now, I'm assuming you've taken a course in quantum mechanics before. Your Schrodinger equation for the free particle as you may remember, looks like this. It's minus Laplacian psi over 2m. And in fact, I should say at this point, if you put back the h bar, there's an h bar here, and then there's an h bar squared here. Right? And so what you discover is that if you want to identify the right-hand side to be kinetic energy, okay, so you see p squared in the position representation is just minus Laplacian. So you see that the right-hand side is just nothing but kinetic energy, but in the position representation. But that works if you stick in an h bar, right? So in quantum mechanics, so in fact, here there is no h bar. In quantum mechanics, we stick in. So this is just linear algebra. But in quantum mechanics, then you stick in the h bar and you say if you want to call p, you rescale it by h bar. But then your translation operator will need to have an h bar over here, and then it's d dot p. Okay, so this would be t. For once, I write down the h bar, but I just want to show you that actually the h bars cancel out. Right? So again, remember that I stick in the h bar in the derivative, but so there's a hidden h bar here, and then you have to pull out one of the h bar so that actually the h bars cancel out. And then this guy we call momentum. In other words, if you ask the question, what is the dimensions of this guy, then you find that this is actually momentum. Okay, momentum is mv, right? So it's mass times acceleration. Right? You can check. H bar is energy times time. Which I think is 10 to the minus 34 joules seconds or something like that. And then gradient is 1 over length. So you can work out energy times time divided by length is that acceleration. I'll leave it as a homework for you guys to discover. But that's the relationship, right? That's why we stick in the H-bar, because we want to identify the right-hand side of the Schrodinger equation with kinetic energy. So i.e. kinetic energy.
Professor,
Yeah.
it is velocity, not acceleration.
Sorry, thank you. Yeah. I was thinking about force. Or speed, right? Because we're just doing dimensional analysis, so it's just speed. Yeah, thank you. Yeah. Okay, any questions for me? Okay, so now we know that P is Hermitian, Pj is Hermitian in infinite flat space because the translation operator is unitary. So if it's Hermitian, we're guaranteed that Pj itself must have its eigenstates as well, which I'm going to call K for a reason. We will discover very soon that K is nothing but what we call momentum space. And this K, in turn, is what will give rise to the Fourier transform. Okay, so we'll discover this. So, but for now, we know that there must be an eigenstate. There must be a complete set of eigenstates for P because it's Hermitian. Okay, and so this tells you that we can also try to work out, for example, the commutation relations between P and X. The reason is the following: we have discovered that we can diagonalize P, but we have also known that our position operator has its own eigenstates, the position eigenstates. So the question is, are they simultaneously diagonalizable, right? So are P, momentum, and position simultaneously diagonalizable? Can I observe both of them at the same time? And the answer is no, as we're going to discover. Okay, so how do we do that? So what we're going to do is we are going to do a calculation by taking the infinitesimal displacement again. Okay, so what we're going to do is the following. We're going to take x, I, and then we're going to apply a small displacement, and then I'm going to apply the whole thing to x, the position eigenstate. So let me just write down versus that. Okay, so there are two sets of eigenstates that I need to have some understanding of. And so what's going to happen is that this is going to be, firstly, xi, equals, applied to x plus dc. Okay? And now this is the eigenvalue because I've shifted it. So it's going to spit out xi plus dci, x plus dc. Now let's consider the other way around. The other way around, which is if I apply xi first, before I apply the translation operator. So this is going to give me x. But remember, x is now just a number, so I can pull out xi, x. And then what will happen is that this is xi, x plus dc. Okay. So this is a small displacement, so I can imagine that I can now Taylor expand both sides, right? So xi times a small translation operator is just I minus I dc dj pj. And higher order terms acting on x is equals to xi plus dci, and this guy I'm going to Taylor expand it as x plus dcj partial j acting on x higher order terms. Okay. And then this guy, this guy I can also Taylor expand. So this is identity minus I dcj pj higher order terms, all acting on xi, and then this is equals to little xi, and then this x plus dcj partial j x higher order terms. Okay. And so what I'm going to do is I'm going to subtract both sides and only keep up to first order terms. What you notice is that the zeroth order term cancels out because this is identity times xi, this is identity times xi. I'm sorry, there's an x here. So it will cancel out. And let me try to run it better. xi, x. Yeah. And then, similarly, the zeroth order term here is xi, x, and then this is xi, x, right? So when I subtract, these two lines, what do I get? I get minus I, x, dcj, and then I get x, I, pj, okay? And then minus I dcj is common to both of them, but now I have p minus pj xi acting on x, okay? That's the left-hand side. And then on the right-hand side, I get what I have first. Remember, I care about only the first order term. So what I have over here is I have this guy times that guy. dc is equals to dci times x, and then this times that, okay? Yeah, plus x I dc j dj. And then minus what? This cancels out already. Minus the first order term here, which is minus xi dcj dj, all acting on x. Okay? So we can continue over here, and you see that this cancels out. I get what? I get minus I dCj xi pj minus x minus pj xi ijji acting on x, but this is a base, this is arbitrary. You see, this is arbitrary, but it's a basis. So therefore, it has to be that the operator on the left-hand side must be equal to the operator on the right-hand side, which means that this is just equals to dc, let me write it this way, j, and then Kronecker ji, because I know it's I, but I'm just going to contract it so that I have dCj on both sides. Okay, and which means that now I can multiply, I recognize this as just nothing but a commutator, xi commuted with pj, and if I multiply I on both sides, I get I Kronecker ij. Okay. So this is still linear algebra. Okay, so this is just linear algebra. But remember, in quantum mechanics, we stick in an h bar here. So what I do here, I just take this equation and I multiply it throughout by h bar. So in quantum mechanics, this will be xi pj, but now pj has an h bar hiding inside it, so therefore this will be I h bar delta ij. And that's the form that you guys might be familiar with, right? And in undergraduate quantum mechanics, you may have just been told that that's the way it is. But actually what you see is that it's something that can be derived. It's not independent, it's not an independent postulate of quantum mechanics. It comes from studying translations acting on these position eigencamps, right? So the answer, and furthermore, this tells you that the fact that these guys don't commute tells you that you cannot simultaneously diagonalize x and p. You cannot simultaneously diagonalize. Then there's a question. Well, if that's the case, then I need to find out how to change my basis, right? So sometimes I might work in position basis, sometimes I might work in momentum basis. And now the question is, how do I change between them? Right, so the question is, how to change basis. Okay, so I know I'm running out of time, but let me just do one more thing, which is that since we know what the momentum operator is, let's just do one thing, which is very simple. Solve a very simple differential equation. So let me finish and then I'll let you guys go. So we know the following. Let's consider the following object. So I take the matrix element of Pj sandwiched between the momentum eigenstate and the position eigenstate. So this is the position eigenstate, and this is the momentum eigenstate. Okay. So there are a few things we can do to it. Firstly, we know that I can add this guy to the right, and this will just spit out kj x k. Okay. But on the other hand, I can add it to the right, to the left, and we've just discovered today that pj is just a derivative, right? I think I erased it already, but it's basically acting on the left. This would be minus I partial j x k. So what we discover is the following, that the overlap between the momentum eigenstate and the position eigenstate actually satisfies a very simple first order differential equation, right? So in fact, it satisfies this. It satisfies partial xj x, okay, is equals to, let's multiply I on both sides, kj xk. What's the solution? What's the solution? Forget the fact that, let's just look at one variable, right? So let's just do it for one variable. Xk equals to Ik xk. What's the solution? Exponential, right? It's because it's just a first order equation. You can just integrate it right away. So this guy, xk, so if you have a first order equation, you have one integration constant. So you get chi, let me call it c, e to the I k x. Right? And you can test your answer, just differentiate and see whether you get ik out of it. So for the multivariable problem, xk will be equals to some constant times e to the I k dot x. Okay? And so how do we fix this constant? So remember the following. So remember that the matrix element between x and x prime is a delta function. It's a delta d of x minus x prime. Okay? This is the identity operator, essentially. Identity operator in position basis. But now I can insert a complete set of momentum eigenstates. And I got x, k, k, x prime. Okay? But we just solve for these guys. This is the plane wave, that's the complex conjugate, right? So this is in fact integral over k and then I have a c, so it will be c squared times e to the I k dot x for this guy, and then there will be a complex conjugate here. This is why I get an absolute value squared, minus x prime. Okay. But this is a delta function, so in fact, if you remember, we wrote this down a while ago, maybe on Monday or the week before. If this were 1, then this is exactly the delta function. Okay, so that means that c, absolute value of c is just 1. And so usually we choose the phase to be 0, so therefore c is just 1. Okay, so in fact, we choose, this is a choice, that xk, let me write it here, we write xk to be just the exponential itself. Okay? Any questions for me? No? Have you guys seen this before? Yeah? Yes? Who has seen this before? Only 2 of you. Okay. Have you seen it before? You? No. Oh, you've seen it the last time because you talked, yeah, okay. Okay, all right. See you guys next week.